Welcome to This Explainer. Today, we're diving straight into one of the most fascinating questions in science. How do the microscopic interactions of billions of tiny particles actually create the rules for our macroscopic world? Think about it. When you look at a smartphone, a magnet, or even just a piece of glass, you're looking at something fundamentally mysterious. Sure, we know they're made of atoms, electrons, and nuclei, but knowing the rules of a single isolated electron doesn't actually tell you how a billion of them are going to act when you put them all together. Today, we're exploring the realm of condensed matter physics, the field that explains exactly how these massive crowds of particles self-organize into the materials that literally define our modern lives. Back in 1972, the Nobel laureate P.W. Anderson made this incredibly profound philosophical observation. He simply said, "More is different." And what he meant was that the laws governing a complex macroscopic system absolutely cannot be reduced to just a basic extension of the laws governing its individual parts. Think of it like a city. You can't understand the complex, bustling behavior of a whole metropolis just by studying the psychology of a single person sitting alone in an empty room, right? It's the exact same thing in physics. When you pack massive numbers of particles together, entirely new laws, phases, and behaviors emerge that just do not exist at the level of a single atom. So here's our roadmap for today. 1. When more is different. 2. The birth of quasiparticles. 3. Phase transitions and order. 4. The superconductivity miracle. 5. Topology and 2D materials. And 6. Building the quantum future. All right, let's jump straight into part 1, when more is different, looking specifically at microscopic structure. To really wrap our heads around this, we have to completely shift our perspective. Instead of looking at one lonely particle floating in a vacuum, we have to look at the periodic lattice of a crystal. Inside a crystalline solid, atoms are arranged in this perfectly repeating unit cell. And because of this perfect repeating pattern, what physicists call translational symmetry, electrons don't just stay trapped around a single nucleus anymore. Instead, they exist in what are known as extended block states. They spread out, forming these broad energy bands that flow throughout the entire crystal. And depending entirely on how those energy bands are filled, this macroscopic architecture dictates whether the material in your hand is going to be a highly conductive metal, a semiconductor, or just a complete insulator. Moving right along to section 2, the birth of quasiparticles, where we'll look at emergence excitations. Imagine an electron moving through that repeating crystal lattice we just talked about. It definitely doesn't act like it would in empty space. It gets constantly pushed and pulled by the periodic potential of all the surrounding atoms. And because of this, it responds to external forces completely differently. The curvature of its energy band literally changes how heavy it feels. It takes on an entirely new effective mass. It might act much heavier or much lighter, kind of like an electron putting on a heavy-weighted vest or tying itself to a helium balloon. So here's the real kicker. As an electron is dressed by its interactions with lattice vibrations and other surrounding particles, it emerges as something entirely new, a quasiparticle. This is a total game changer. We aren't just dealing with fundamental particles anymore, we are dealing with emergent phenomena that act exactly like their own unique entities. They carry a renormalized mass, which basically just means their mass is adjusted by their environment, and they exhibit completely different behavioral traits. And this beautifully illustrates how collective behavior gives us new realities. Take a look at some of these examples. When an electron is missing from a nearly filled band, that empty space acts perfectly like a positively charged quasi-particle called a hole. In magnetic materials, a wave of flipping spins propagates through the system as a magnon. The quantized vibrations of the physical lattice itself behave as phonons. And it gets even wilder when we look at strongly correlated materials, like Mott insulators. In these systems, standard independent electron theory fails completely. The electrical repulsion between the electrons is so unbelievably strong that instead of flowing freely like they would in a metal, they become localized. They act like a gridlocked crowd of cars stuck in rush hour traffic, completely turning what should be a conductor into a rigid insulator. That brings us to section 3, phase transitions and order, dealing with collective changes. Now, we're all familiar with water freezing into ice, but in condensed matter physics, phase transitions involve incredible leaps in collective order, like a magnet suddenly aligning all its spins the moment it drops below a critical temperature. But what's truly mind-blowing here is the BKT transition. Physicists Kosterlitz and Thales proved that conventional long-range order, where everything just points in the exact same direction, isn't the only option out there. In two-dimensional systems, phase transitions can be governed entirely by topology. At really low temperatures, you have these paired vortices and anti-vortices. Think of them like microscopic hurricanes spinning in opposite directions, locked tightly together. But when you heat the system up, thermal fluctuations tear them apart, destroying the quasi-long-range order. This was huge because it proved that topology acts as a massive organizing principle in physics. Okay, on to section 4, the superconductivity miracle, focusing on coherent condensates. Let's think about this logically for a second. Electrons are negatively charged. Basic electromagnetic forces dictate that they naturally repel each other. So how on earth do they suddenly decide to form a coherent condensate, pairing up to carry an electrical current with absolute zero DC resistance while perfectly expelling magnetic flux, a phenomenon we call the Meissner effect? It honestly seems to defy standard logic. Well, the BCS microscopic theory solves this puzzle beautifully. Picture this. As the first electron zips through the crystal, its negative charge slightly pulls the positive lattice ions inward, creating a brief, tiny distortion. This distortion, this phonon or lattice vibration, creates a fleeting pocket of positive charge that actually attracts a second electron. Against all odds, this vibration mediates an effective attraction, binding those two electrons into what's called a Cooper pair. These pairs drop into a lower energy state with a protective energy gap that suppresses low energy scattering. It literally allows them to flow completely uninterrupted. It's this incredibly elegant microscopic dance creating pure macroscopic magic. Next up is section 5, topology and 2D materials, where we examine global wave functions. When we compare some of these revolutionary materials side by side, the fundamental differences are striking. Take a topological insulator. It's incredible because its bulk is a complete insulator, but its edges are literally forced to be highly conductive, protected entirely by the material's quantum topology. The surface states often resemble 2D direct fermions, meaning they behave as if they have completely lost their mass, allowing them to move at blistering speeds. Then we have graphene, which is just a single layer of carbon arranged in a honeycomb lattice. Because of its unique structure, its electronic dispersion is approximately linear. That means its electrons behave as massless Dirac quasiparticles. So not only is it highly conductive, but it possesses extreme mechanical strength and thermal properties that are almost unrivaled. Now, when we look at phenomena like the quantum Hall effect in two-dimensional systems, the conductance becomes quantized in exact units. This isn't just some random occurrence, it's deeply tied to a topological invariant known as the Chern number. Because these topological invariants are discrete integers, meaning they jump rigidly from 1 to 2 to 3, kind of like climbing stairs rather than walking up a smooth ramp, the resulting electronic states are virtually immune to many forms of physical disorder or imperfections in the material. It's quite literally a mathematically protected state of matter. Finally, section 6, building the quantum future, where we explore the real-world technological impact. The reality here is that translating quantum interactions into macroscopic properties is the absolute bedrock of modern technology. I mean, without understanding energy bands, we wouldn't have semiconductor integrated circuits, which means no computers, no internet, no smartphones. Understanding collective spin gave us magnetic data storage and spintronics. Superconductivity gave us the high-field magnets required for MRI machines that are saving lives every single day. And looking ahead, grasping topological and 2D materials is exactly what's paving the way for low-power, flexible electronics and the immense, game-changing processing power of future quantum computers. But here's the catch. Theory and lab discoveries are really only the beginning. Discovering an astonishing material like unconventional, high-temperature cuprate superconductors is only half the battle. The engineering challenge is massive. We have to figure out how to actually synthesize these complex phases without relying on the extreme pressures or near absolute zero temperatures that you can only get in a laboratory setting. Scalability, environmental impact, and real-world stability, those are the crucial bridges we must build between theoretical physics and mass manufacturing. And that leaves us looking at a truly exciting frontier. As we continue to uncover new non-equilibrium materials, strange magnetic phases, and highly tunable Moiré heterostructures, we're effectively uncovering completely new forms of collective intelligence in physical systems. So think about this. If we've already gotten superconductors and semiconductors just from basic atomic organization, what unimaginably bizarre and powerful macroscopic realities are just waiting to emerge from the quantum materials of tomorrow? It's a thrilling question. Thanks so much for joining me on this explainer. Keep questioning, and as always, keep learning.